Okay, so this is the dollar bill drop problem. So if you hold the dollar bill right at the top of your friend's fingers, like so they have to grab it like this, you leave the bottom of the bill right above their hand and drop it. Can they catch it? Or will it go right through their finger? It's got to be a crisp bill so that it drops well. Anyway, what we know is that a dollar bill is 15.5 centimeters in length. And we know the average human grasp time or reaction time is 0.20 seconds. So can they catch it or will it fall through their fingers? So how do we solve this problem? Well, we draw the picture and we think about, okay, we want to know if they're going to grab it in time. So what we need to know is, in that amount of time, how far will the bill fall? That's how we have to think about this problem. So given that information, we have to think about, okay, so if I want to know if they're going to grab it, I want to know how far is that bill going to drop in 0.2 seconds. So will it be at this point or at this point where they can still grab it, or will it have gone all the way through their fingers in 0.2 seconds? So let's look at how we solve that. So let's go over here to our given. We know the time that it takes to drop. We know a falling bill is going to drop under the influence of gravity, which is 10 meters per second squared, and its initial velocity is 0. How far will it drop in 0.2 seconds? What's the distance? Okay, so our equation is for distance. We're going to use the distance equation, okay, and we're going to plug everything right into this. There's no need to manipulate. Yay, we don't have to isolate any variables. This is already ready for us. So the hardest part of this was thinking about how to solve it. Okay, we plug and chug. That first part of the equation comes out because initial velocity is 0, so we just get d equals 1/2 gt squared. Okay, fill it in. Plug 1/2 gt squared. Chug, bring it on through. We end up with 5 times 0.04, which is 0.2 meters. Oh, wait a minute. Tricky, tricky. It falls 0.2 meters, but when we think about how long a dollar bill is, we talk about it in, where is it? Oh, here in our information. We go back to the original problem. Wait a minute, it's 15.5 centimeters in length. Well, we got to think about how to compare centimeters to meters. So you know what we have to do? Your favorite thing. We need to convert meters into centimeters. So if you remember, you're just going to slide the decimal 2 to the right. Kilo, hectodeca, unit, deci, centi, milli. King Henry died by drinking chocolate milk. But if you don't remember to slide it 2 to the right, you can use this good old conversion factor. 0.2 meters times, we're getting rid of meters, so they go in the garbage in the denominator. We're moving into centimeters, so that goes up on top. We throw away the garbage in the bottom. We take what we want to, we put what we're going to on top. 0.2, there's 100 centimeters for every 1 meter. So we're multiplying by 100, which is the same as sliding the decimal 2 to the right. It would fall 20 centimeters in that amount of time. 20 centimeters. So, are they going to catch it? They're not going to catch it because the length of the bill is 15.5 centimeters. It is 4.5 centimeters through their fingers already. Too bad, you win the bet. Try that with a $100 bill, and then you'll win $100. All right. Onward.